feed on stage one. How many did we take? 1, 2, 3, 4. Well, this is a tad high. That was way low. So I fiddle around and I get it worked out. So that's how you do the prediction problem. Now, you would come in here and say, well, you know what? Had you put that feed on a higher stage, you could have done much better, everything else the same. And you're absolutely right. I could have done much better, everything else the same. So, but nonetheless, if the column is built and I see the feed going in on stage one, I've got to put it in on stage one. Now, there's something called stage efficiency that helps us correct for the fact that we've been assuming equilibrium all along. It's a funny sort of thing. It's sort of a friction factor sort of thing. That is to say, you've got to get data, estimate what it is. But here's how it's defined. E, the stage efficiency, is defined for, here's a stage I. Here's yi rising off that stage. Here's xi falling. And you've arrived at xi. You're about to calculate yi, and you say, there's a stage efficiency, is there? Yeah, the true yi minus yi minus 1. So there's a yi minus 1 coming on here that somehow you've already calculated. The true yi minus 1 is the yi star minus yi minus 1. Yi star simply means that xi here and yi star are on the equilibrium curve. So these two are in equilibrium. So when I want to calculate the efficiency, maybe it's 50%, I get to go 50% of the way that I would have gone before. So here's what it looks like on a graph. So I'm doing a problem of some sort or another, and I've been moving along here, and maybe this is the line right here, and maybe this is the equilibrium curve right here, and maybe I've arrived at a material balance point right here. This would be the point whose coordinates are xi, yi minus 1. So this value right here is yi minus 1. This value right here is xi. You say, okay, I'm getting ready to take my equilibrium step. Well, if I took my full equilibrium step, that would be yi star. But it tells me I better hadn't do that. I better go only part way from yi minus 1 to yi star. So I said, okay, I'll do that. There's 75% stage efficiency. Then I continue and do that. Made a material balance. The new y star is here. There is 75% stage efficiency. If I'm in the top, I do the same thing. Here's the top. I might be here. I'm looking to go there. I go 3/4 of the way and make a material balance. So I've accounted for a stage efficiency. If the stage efficiency, our columns in the lab have stage efficiency, well, we don't really know. Somewhere around 50%. Now, how do you obtain a stage efficiency? Well, there's several ways. In the back of King, in one of the appendices, there's a method given that the chemical engineers have put a lot of money into, the oil companies, I guess. And it's a way of predicting stage efficiencies based on how the stage is built, and so on. Another way, so you can go back there and try that. Another way is you might say, hey, I know what I'll do. I'll come out here and I'll run my column. I'll return everything. I'll boil some up, I'll return everything. I'll sit here. I know the number of stages. I will measure this, and use those measurements to, given the number of stages, to predict the stage efficiency. So you can always, and in fact, that's what the students, one of the things students do in the lab is they probably run this thing by returning everything and get a stage efficiency. Okay, so that, we pretty much have all of the basic stuff under control. There's one more basic thing to do, but let's don't do it right now. The remaining basic thing to do is to remove the equimole overflow assumption. Let us don't do that right yet. We'll start that in a minute, maybe. Here is a problem that I'm not going to say too much about, but it's called the Ryan problem. We might even say this is Ryan's first problem. Ryan says one day, why are you wasting time with a condenser? So Ryan says, get rid of that condenser, it's a pain in the neck. So you got this column you're dealing with. Let's say you got a 5-stage column, and you want to know what it does. So as an example, take a 5-stage column. You want to know what it does. You give it 100 moles per hour of feed, maybe the feed composition's a half, and you're going to stick the feed into the reboiler. Okay, so here we are. We have this column sitting here. We're going to stuff the feed into the reboiler, 100 moles per hour. It doesn't matter what the condition of the feed is, because I'm stuffing it into the reboiler, and the only thing that cold feed will cause you to have to do in this case when I'm sticking in the reboiler is just put more heat in there. Heat in to vaporize, heat in to heat, get rid of the sensible heat of the feed if it's cold liquid. So here it goes, up here, down here, up here, down here, stage 1, stage 2, stage 3, stage 4, stage 5. Brian's going to take his product out here. Okay? He says, what are you doing with it? Why are you bothering with a condenser? So somebody comes along and says, well, where do I get the ship to send liquid back to the column? Brian's got an answer for that. He not only wants you to get rid of the condenser, he wants you to get rid of the insulation. So you remove the condenser, out with the condenser, and off with the insulation. So you strip the insulation off. Now it's running there losing heat. Ryan's pretty happy now, because when you lose heat, you got to make up for the heat loss by condensing vapor. So Ryan says, I think maybe you're going to lose 20 moles per hour here, 20 here, 20 here, 20 here, and so on. 20 off each stage. So the flows now look something like this, just to get an idea of what might be going on. The flows now look like this. And Ryan says, of course I'm going to have to tell you the boil-up rate, because this called, so he says, go ahead and boil up 150. Take some product off here, put 100 in there. What I want to know is what's the YD shooting out the top and what's the XB coming out the bottom, as well as the flows. So here's what we do. We say, here's our column, 150 coming up. And you're condensing, you're losing 20, so you have 130 here. You're losing 20 again, so you have 110 here. You're losing, you got 90 here. You got 70 here. You got 50 coming out the top. So right away, you got a 50 mole an hour product coming off the top, so you got a 50 mole an hour product coming off the bottom. So, so this is 20, 40, 60, 80, 100. Dropping into here where you're feeding 100. And so you're taking, now why don't I like this? You're taking 50 at the bottom, that's right, everything's fine. So, everything's in balance now, according to our all of our full assumptions and everything. So we've got a column whose feed location is known, whose number of stages is known, whose boil-up rate is known, whose reflux ratio we don't care about because there isn't, it's all internal reflux due to heat loss. And the question is, what's this thing do? Now, if there's any suggestions, I'll listen to them. If there's not, I'll let you guys think about this over the weekend. I must say that I have not done anything that changes the pattern of the argument. So I want to know what I got to do graphically to predict what this column does. And there is no new tricks. Well, I wouldn't call it a trick. So this is the Ryan column. This is a problem for your enjoyment. So I thought maybe we would, before we, well, we're going to talk about two-feed columns next in anticipation of trying to decide how we might separate an azeotrope. But let's don't do that. Let's say we have, so far all we've said is, I know the latent heats of the two species, and I think they're pretty much the same. It's the only data I want right now. Now, there's several cases. One case is, suppose all the data I have is the latent heats, but the latent heats are not close. Well, there's something you can try and do in that case, but let's skip that for the time being. Let's move on to the case where we have complete data. So I'm going to set the pressure. C is equal to 2. I'm no longer going to assume anything about the lambdas. I've got complete data. So I have y versus x. And I've got enthalpy data. So here's my enthalpy data, H or H versus X or Y. And maybe it looks like this, maybe it looks like this. This is vapor. This is liquid. This is two-phase. This is the vapor saturation curve. This is the liquid saturation curve. If I wish, I can put tie lines on here. For example, I can go to an X over here, read off the corresponding Y, go to that same X here. This then point would be X and H, and the point that comes with the Y would be Y and cap H. I would call this a tie line connecting an equilibrium point with an equilibrium point. These are the latent heats of the pures. This right here is lambda 1. This right here is lambda 2. And I'm going to try and do something. Now, I badly need a balance that tells me how the material and the heat balances around my column. So that's the position I find myself in. So let's see how we might begin with this. Okay. I'm going to take the top of the column. Now, I'm going to imagine we are trying to design a column. We're looking for the number of stages, the feed stage, and so forth. So let's suppose we have a, let's suppose we know the feed, we know the feed composition, we know the feed end value. So far, so good. I will begin with QD, but I'm going to imagine I've got a total condenser. And I'm going to imagine that I've got a E equal to 1. So I've got equilibrium stages. I'm trying to account for the fact that the material balance is no longer a simple thing. So I'm going to go to the top of, and I got product specifications. So XD is assigned, and maybe XDE over ZF is assigned. So from these givens, and what we're going to go do is we're going to go try and find the number of stages is needed, and the feed stage location, and the QB. So I'm given the reflux ratio all right. I'll need to connect that to QB at some point, QD at some point. But right now I'll work in terms of QD because we're going to make an enthalpy balance. So we're going to start. We'll go around the top of the column like we've always done. So what have I got? I've got F, well, no, I better draw. I'm in the top of the column here. Feeds down here somewhere. This is coming out, this is condensing, this is going back, this is my product. Presumably I know each of this distillate, I know. I've assigned XD. I'll denote the product rate by D. As a matter of fact, I know it from the product specification here. These two tell me immediately D, so I know D. Let me pretend like the Q that has to be removed here is QD, negative. So I'm going to make my balances around here. And I'm going to look at them, and then I'm going to do one of our favorite old tricks. So I've got a Y coming on here, an X going off here. I've got a V coming on here, I've got an L coming off there. This V and this L, I've got no reason to assume they're constant. No reason to assume constant L and V, so I won't. But that won't affect how I write the balances around here, so I'm going to write balances around this part. So that'll be our first move. What time you got, Joe?
43.
You got a test?
No.
Yeah. Yeah. Okay. VJ, I'm just going to let them to you. Let me ask you this question. Is this going to be the last problem on the first part of the course?
Yes.
Okay. So the next test will probably be a what? A distillation problem of some kind?
Yes.
Okay. So you need to know that. Okay, man.